Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera everyone. Now it comes to our last subtopic for semester 2, that is chapter 9. It's nuclear and particle physics. For this chapter we have 3 chapters. We only have 2 subtopics that covers the calculation. So the first subtopic is the binding energy and the mass defect. The mass defect is the difference in total mass of the nucleons and the actual mass of the nucleus. So this is the equation of the mass defect. It's delta M is equal to Z number of proton plus number of neutron times the mass of neutron minus mass of nucleus. But if the question gives us the atomic mass, so we're going to use this equation. So the difference between the previous equation and this one is here is mass of atom and mass of proton to be substituted with the mass of hydrogen. Okay, so these two equations basically given in the formula list. The other option, but the term mass of nucleus here is to be found first using this equation. So mass of atom minus Z mass of electron. When you've got your mass defect is basically to be used for calculation of the binding energy. So binding energy is the energy bound between the nucleons in the nucleus. This amount of energy is energy required to break the bond or to combine any nucleons to be a nucleus. So this is the formula, the basic formula for binding energy is EB equal to delta MC squared. And we have another option here. So these two equations are to be used for different condition. That is, the first one is when you have your mass given, your mass defect given in kilogram. Then you use the basic equation delta M is equal to C squared. C is 3 times 10 to 8, the speed of light, squared. Then your answer is going to be in the unit of joule. If you have the mass defect in the unit of EMU, then you can straight away multiply with 931.5 MeV. Hence your final your answer for binding energy is going to be in mega electron volt. If you want to convert from mega electron volt to joule, that is going to be, for example, 1 mega electron volt. So 1 mega is 1 times 10 to the power of 6. Electron is 1.6 times 10 to the power of negative 9. So your answer of this multiplication is going to be in the unit of joule. And we have another conversion. If you want to convert your mass from U to kilograms, so the conversion is 1 U is equal to 1.66 times 10 to negative 27 kilogram. So this is how you can multiply any numbers of mass in the unit of U with this number. Then you get your mass in the unit of kilogram. So that is the first subtopic. The second subtopic for chapter 9 is radioactivity. So we focus on the process of decay, okay, the decay of certain nucleus. So when we mention decay, we have to understand that we have a few types of decay. For example, we have alpha decay, beta plus, beta minus, and gamma decay. It means here that during the decay process, these 4 particles is possible to be emitted. So this is the example of reaction equation for the decay reaction. For alpha decay, we are basically balancing left side and right side of the equation. So let's say we have a nucleus of A with this nucleon number and proton number. Then to balance the equation, as we know this is an alpha particle emitting from this reaction, so your new particle is going to be 230, okay, and your Z is 8. Then if you total up these two numbers, you'll get this number. So same goes for the reaction of beta minus, okay, 234, 2340, 10, 11, negative 1, so that they are balanced. So this is beta plus and this is gamma. So we don't have any proton number, or nucleon number for gamma. Okay, so that is the decay reaction. So when we discuss about decay, we have the equation of decay equation or radioactivity equation. First, we have dN over dt. So this is the decay rate. The equation is negative lambda n. So lambda here is not the wavelength. It is equal to the decay constant. The unit is per second. N is the number of nuclei, number of remaining nuclei after the decay. If you are given the mass of nuclei, okay, in the question, you have to first know that we have this equation. So from this equation, okay, number of nuclei per Avogadro number is equal to mass of nuclei per molar mass of that nuclei. If the question give us the mass, then you can calculate the number of nuclei so that you can use in this equation and also some other equations. So molar mass normally is not given directly in the equation, but you have to know that the molar mass is equal to the nucleon number. So let's say we have uranium 235, so it means that the molar mass is 235 gram. The decay rate is also have the same meaning as activity. Okay, we have activity. So activity is equal to decay rate. So that's why we have the same equation lambda n. Or if you want to use this equation for initial activity, so it's going to be A naught equal to lambda n naught. N naught is the initial nuclei. So the unit for activity is equal to the decay rate is decay per second, or it is also equal to becquerel. This is the SI unit. But sometimes question may give you the unit of activity in the unit of Curie, Ci, and this is the conversion between the Curie and becquerel. The equation for activity is also can be expressed in the terms of A equal to A naught exponential negative lambda t. So t is the time taken for the process of decay, and A naught is the initial activity. And also you are having an equation for the number of remaining nuclei, and if we compare these two equations, they have the same pattern of equation. It's not the same equation but the same pattern. This equation is derived from this equation A is equal to lambda n. Okay, and we have half-life. So half-life is the time taken for the nuclei to be half from its initial nuclei. This is equal to ln 2 over decay constant lambda. And that's it for 9.2. So this is all about chapter 9, the last chapter for this semester. Okay, thank you.